it again. We actually didn't say yes, okay. There we go. Welcome. Oh, that reminded me. I wanted to show you something on ClickUp, but now I can't remember what it was. Blackboard. Sign in. So there were a few things that were updated to ClickUp. I'm not sure if David and Brent made any updates for the pracs, but just from my side, there were a couple of things that I changed. So under course information, eventually, I did add the, where are they? Oh wait, where are they? There we go. The class reps. Their email addresses where you can contact them are over here, so if there's anything important happening in the class or whatever that you want me to know about, but that you don't want to come and tell me yourself, please get hold of one of these folks. And again, thanks very much to these folks for being willing to help. Really do appreciate this. I know the class reps kind of, some idiot has to do it. It's actually something that can be really valuable to us as lecturers. So thanks very much to those folks who are willing to do that. And then the second thing was I did set up a Telegram course group, as I said yesterday, so you guys can use it to just share information about the course, chat to each other, ask questions, whatever. We're not going to moderate this. We're not going to look at it. If there are problems, then yes, I'll have to get involved. But the idea is this is for you guys. Please use for whatever you use it for that is useful. Every year the students use it for different things, but a lot of the time there's very good stuff. Like I say, that example that I like to quote of the, where's the semester test being held? Sort of half an hour before the semester test starts. And someone actually responded. So whatever you want to use it for, just go there. That link should take you to the group, and then you can just join. Last time I looked, I was the only member, so I'm getting lonely. So please, somebody join. All right. Yes?
Yesterday, at least again, I told the people trying to click on the link, but it just didn't work.
Oh, I will try to fix the link and repost it. Thank you. Useful feedback, appreciate it. All right, so don't click on it now. I'm not going to do it now during the lecture. I'll see if I can fix it after this. Sorry, didn't mean to do that. With any luck, you should be able to go, copy that thing, where'd it go, and paste it there. Yeah, that works. So, in other words, that thing's correct, but the link is wrong. How is that even possible? What in blue blazes? Okay, with any luck, now it should work. All right. So, in case anybody doubts that I respond to student comments, well, there you go. All right. I hope it works now. I had a couple of people ask me, is there anything you need to prepare for the prac session this afternoon? No, it's a pre-prac lecture to explain to you what to do. The open lab sessions are open lab sessions. The ALs will be there to help you. It's not that you have to sit there and go through a massive demo or something. That's why we're using the online system, so that we can evaluate your work in what is hopefully the quickest, most painless way possible. As always, if anything happens, if there are any issues, please let us know. But yeah, that should be that. Anything from your side about the course? Yes, sir? It'll be in the ABC labs, yes. I had a look the other day because I wanted to host a meeting with my students, and every single lecture hall on the Hatfield campus is permanently booked, except for late on a Friday afternoon. It's ridiculous. Yes, ma'am?
Pre-prac lectures in the net labs.
Sorry, the net labs, not the ABC labs, sorry. I always think of ABC computer labs, electronics labs. Thank you. Remember I said I might make mistakes? Yeah, guess what? I'm human. All right. Anything else? All right, then. On to what's actually part of the course. So, yesterday we had a quick look, well, relatively quick look. And sorry for missing the audio recording yesterday. Yeah, there's an issue with the audio when I plug the HDMI in, when I don't. Sorry. I'll try to not do that again. The lecture recording for yesterday doesn't have audio. I'm not going to look for it now. But I did post the last two lecture recordings. The one just doesn't have audio, so sorry about that. All right. So we had a look at what is AI, and we realized it's really difficult to see what AI is. It's very difficult to come up with a simple definition. And what we're going to have a quick look at today is to say, well, one of the reasons for this is that there are a very large number of relevant fields. So these are all fields of study in their own right, massive things in many cases, that are relevant to the consideration of AI. Now there's sort of two ways I want to look at this. The one way I want to look at it is to say that AI is that broad. Yes, it is. But secondly, to say, a lot of the times, if you're looking at something that's AI, you shouldn't be looking at it as AI, you should be looking at it, say, maths, because there's actually a nice mathematical solution for it. So see this both as a list of fields that have an input to AI, but also fields that have kind of solved some of the problems that we sometimes think are AI, or give better solutions than AI tools. So just keep that in mind as we go through this list. So the first one, which I'm sure will surprise practically nobody, is philosophy. Sophie. After yesterday's lecture, is that spelled correctly? Yes, it is. So after yesterday's lecture, as you realize, we're looking at things like what is thought, what is intelligence. And if you're going to think about thinking, you're working in philosophy. So philosophy definitely has a lot of relevance to AI. And we're looking at things like, can we create rules to draw valid outcomes? So things like logic, as far as I understand it, originated, if you go far enough back, in philosophy. How do we construct arguments that are defendable? How does the mind arise from the brain? There's a really interesting question. If you look at the bunch of chemicals sitting in your head, how on earth does a mind and intelligence emerge from that? The answer, sort of in brief, is we just don't know. There's other questions that are related to it, like, can you have an intelligence or a consciousness without a body? Do you need to have a body in order to have intelligence? I don't know. This is what we've got philosophers for. So I'm interested in a much more engineering type approach to this, but philosophy is absolutely relevant to this. Other things we can look at are like, where does knowledge come from? Does it only come from experience? Is there some way you can inject knowledge into a system? Things like, does knowledge lead to action? Or more importantly, how does knowledge lead to action? Because great, I've got a bunch of knowledge, but how does it affect what you do? One of the classic examples is if people have a heart condition, you have to change what you eat. You have to change what you live, or you're going to die. It's that blunt. And people really, really struggle with this. You've got the knowledge that my actions are going to kill me. And as humans, we find it really difficult to make that sort of change. So yeah, there's a whole bunch of philosophy in there. Another one, which since we're speaking about logic, and I mentioned statistics yesterday, mathematics. I love telling people, in the United States, they have math. In the rest of the world, we have more than one. We have maths. So, yes. Okay, one person laughed. All right. Okay. If you don't laugh at the joke, at least laugh at me. All right. Got more of a laugh that time. All right, so mathematics. This is things like logic. How do we construct formal rules? How do we construct rules of proofs? So how do we prove things? How do we achieve results? Things like what can be computed? NP completeness. You guys will have done a lot of that with the computer science department. That's really important because if we can't compute something, how do we, do something with it? How do we do something useful? And this will crop up again when we look at why do we want machine learning. And one of the reasons we want machine learning is what if we can't solve the problem? We don't know what the solution is. Well, close your eyes, apply black box machine learning to it and hope for the best. And that works surprisingly well. And then obviously probability, as I mentioned, is dealing with uncertainty. And I wanted to show this because I quote this thing. Not that one, the other one. This one. I quote this multiple times during the semester. So this is actually from a paper of a relatively well-known random generator. And it's the nature of randomness is that anything can happen and sometimes will. And we'll see that crop up again. But yeah, this is actually from a paper on a random number generator, which I thought was quite cool. But the whole thing of how we deal with probability. Probability is, so far, the best tool mankind has developed for dealing with uncertainty. It's an entire mathematical theory. All right, so mathematics is obviously relevant. Another one that is perhaps a bit surprising is economics. Economics. So economics is essentially the study of how we interact with things of value. So how you get the best decisions in order to maximize the value of something. The whole concept that we're going to use quite a bit during the course is a thing called utility. So utility is how good is something, how desirable is something. Sometimes it's measured in money, sometimes it's measured in other thing, but it's kind of the super general term to mean goodness or desirability or, if you will, happiness. So utility theory essentially emerges out of economics. Decision theory, which is a combination of probability theory and utility theory. So the probability of outcomes weighted by their utility and how we can apply that. Again, that comes out of economics. Things like a large economy versus a small economy. So if I had NVIDIA shares, which I kind of wish I'd bought a couple of years ago, if I dumped every NVIDIA share I own, how much effect is it going to have on the market? Absolutely nothing. I am under no illusions about how significant or rich I am. So that's a large economy, when the actions of individuals within that economy have no dominant effect on the result. However, if Jensen Huang, the head of NVIDIA, if he sells his shares in NVIDIA, what's going to happen to their share price? That's a small economy, because now the actions of each individual have a major effect. And yes, I just used exactly the same example of a small economy and a large economy. The universe is complicated, but this whole idea of how these things work and how they interact comes from economics. Game theory comes from economics. So how people will react to different things, what is the optimal response to a given set of situations. And operations research, which if you can give me a good definition of, I'd appreciate it, because I don't have one. It's sort of a study of how we optimize things to get the best possible outcome. On that, you could probably add something like industrial engineering, which is all about optimizing how things work to give the best possible result, optimizing production lines and processes and things to give the best possible outcome. That's kind of relevant here as well. One that will probably not be a surprise is neuroscience. So that's the study of the brain. So how does the brain work? How do insect brains work? How do human brains work? Because if we can do this, then potentially we can recreate that and get something useful. But as I said yesterday, we have this lovely question of, can you understand how a brain works with a brain? Is it even possible? I don't know. Nobody does. A useful thing to speak about here, which is again beginning to crop up in the popular consciousness, is the concept of the singularity. And the singularity is something that people have been proposing for decades now. That at some point, machines are going to get so good, and here by machines I mean, it's agents, that really general term. So agents are going to get so good that they're going to be improving themselves and building other better agents, and we're going to get this massive explosion in the intelligence of agents. So much so that they will absolutely just overtake humans and dominate everything, and all the world's problems will cease to exist shortly afterwards, because the machines will be so intelligent and so powerful that they'll just solve every problem the world has ever seen, including death. And yes, that is one of the things. People will upload their consciousness to machines and never die. That is one of the things that is predicted with the singularity. Is it impossible? Well, no, I don't think it is. It is still, however, a little bit science fiction-y. But it is a concept that does crop up. And yeah, whether it's valid or not, I do not claim enough to know whether that is the case or not. Another field is psychology. And this is trying to understand, let's write stuff first, then. I have this problem. I'm speaking, writing, and trying to think what I'm going to say next, all at the same time. It never comes out well. All right. So psychology is how do humans and animals think? A lot of modern psychology is how do we fix broken humans? And I must say, since I've become aware of the autism spectrum, I'm pretty sure that every engineer ever is somewhere on the autism spectrum. So we're all crazy. The only question is precisely how much and in what way. But don't worry, you're among friends. All right. So psychology is obviously relevant. Another one that is clearly relevant is computer science. Because we are using computers to implement our AI systems at the moment. So how do we build an efficient computer? And literally this morning came from a discussion with a former colleague at the CSR. We were speaking about neuromorphic computing. And the idea is, why are we trying to implement neural networks with digital computers when the model is analog? And apparently if you implement neural networks with analog systems, you get much more efficient results. So this is kind of building into this in this computing science of how do we build an efficient system. So instead of having this very big, heavy digital thing, we can have a much smaller analog thing. But now we have to go and dig up a whole bunch of technology that computer scientists and at least some computer engineers are allergic to. Analog circuit design. So this is a major issue of how do we actually do this? How do we build machines to implement these AI systems in an efficient way? Then, one that is a major surprise, at least it was to me, control theory. So Prof. Craig and Prof. LaRue's life. And this is relevant because it is how things act under their own control. When a system's stable, when a system's unstable, how can we change their stability? It's a whole study of how do we understand things, how they're going to react, and how to modify them to get them to react the way we do. Now, I like this one specifically because there are a bunch of things that we can look at and say, oh, I've got a problem, I'll throw an AI system at it. And the answer is no, just throw basic third-year control systems theory at it and the problem's solved. So that's, I think, quite a big one. Then another one is linguistics. And particularly with the rise of LLMs, large language models, I think you can see why this is relevant. But we associate speech with intelligence, the ability to communicate with intelligence. So how we communicate, how we share ideas, how we formulate ideas does come out a lot in linguistics. Another one I'm going to throw in here, which is not in the textbook. What color should I use? Let's use this horrible color. Okay. Is optimization algorithms. So these are algorithms that you give it some metric of performance, and then essentially it's a black box like this. You've got a measure of performance on the output, you've got a whole bunch of things over there, you tell it, twiddle the things on the left to make the thing on the out as big or as small as you can get. But a lot of the time, this is what we're trying to do in AI. We just want to adjust input parameters to get the best possible output. And I think a lot of AI actually boils down to just applying optimization algorithms. As you'll see when we get to neural networks, training a neural network is just applying an optimization algorithm to a really bad model of a natural neuron. And hey, they work, which is kind of incredible. So the point I'm trying to make here, as I said earlier, is there are a lot of fields that feed into AI. It's not just a simple little thing, it's a bunch of algorithms which I apply on a computer and that's what it is. No, there's a lot of other things that are relevant to this. And bear in mind that a lot of these things have solved problems already that you don't need to reinvent the solution with AI. Something I'm seeing, at least in the papers I see that are published in the last while, is what I like to think of as an apply algorithm X to problem Y paper. It's like, ooh, I found a new algorithm which I haven't heard of before. Ooh, here's a problem it hasn't been applied to before. Ooh, paper. And the value of this is paper. Yeah, okay. Sorry, bit of a sore point for me in case anyone hadn't noticed. And the thing about AI is, yes, you can just blindly apply algorithms to problems. If you don't understand the problem, you're not going to get good results. And where these fields come in is they often help us, they've often delved into specific versions of those problems in so much detail that don't waste your time trying to apply AI to it. Just use the tools that already exist. Yeah, this is something I feel strongly about. And yes, I will say it again. But AI is not the first tool you reach for in your toolbox. AI is the tool you reach for once none of the other tools have worked. All right, because there's normally, if one of the other tools will work, it will give a better solution. Then, we're now going to have a short history lesson, and that was the other quote I had here. This one. I love this comment, because people often tell you history repeats itself. No, it doesn't, but it does rhyme. And what's absolutely staggering about this is how what we're seeing happening right now, this is not the first time this has happened with AI. This is absolutely amazing. I'm getting bored of black, so let's go for red. Okay, AI history. So this is a really short, really incomplete, really abbreviated, oversimplified history of AI. But let's run through it anyway. It's not that boring. I just said, coming from somewhere. All right. So, the first things behind AI, the initial developments were sort of during the 1940s and especially the 1950s. Why? That's when computers first became available. The first computers became available in the 1940s, Second World War especially. They were all classified. People didn't even know they existed. After that, the research started getting out. So we have the interesting situation where ENIAC is widely recognized as the first computer to run stored programs. But actually, Colossus, the thing the British built during the Second World War, beat it. But it was classified. So people only found out about that quite recently. So when computers started arriving, people obviously started asking, well, how can we use these to try to emulate intelligence and try to create intelligent systems? So initial ideas and this thing started happening, and we're going to see some examples of these in the search algorithms we look at in the beginning of this course. Now, these are things that often date from the 1950s. Are they irrelevant? No! They're still absolutely relevant today. So we had these initial ideas, let's just say that. We had the initial ideas in the 1950s. We also had things like the McCulloch-Pitts neuron, which is the standard basis of neural networks, was developed in the 1950s. They just didn't have the computing power to simulate more than one neuron at a time, and they didn't have the algorithm to train it, the backpropagation algorithm. So those two things changed. But the initial ideas were formed then. And this is when the era when you have people saying, self-driving cars by the end of the decade. And yes, we're talking the 1950s. Here we are, how many years later, and self-driving cars are still not an everyday reality, and even in the cases where they are a reality, they're not terrible. So the problem was, people looked at this thing and said, oh, here's an algorithm which can solve amazing things. Let's look at what it can do. For an example, something I read once was that in the 1950s, if you'd said to someone, you will be able to use a machine to book an airline ticket, they'd have said, that'll have to be an intelligent machine. Nowadays, we understand that that is not the case. But that's because we have a number of decades worth of, I'll get you in a sec, a number of decades worth of additional knowledge that the people in the 1950s didn't have, because they were still at the beginning of all this. They were still at the beginning of computers, let alone AI. Yes, sir?
So I'm a bit confused about the word neuron and Neuralink and how, basically what's a neuron?
Okay, so the question is, what's a neuron and what's a neural network? We'll get back to that in detail later. So you've got something to look forward to. Right. So the problem that happened here, and the big issue about this sort of first wave of AI was, people looked and said, look at the problems we've already solved. By the end of the decade, with self-driving cars, we do all these amazing things, because they didn't understand that they didn't understand the problem. And the problems turned out to be a lot more complex. And so for the first time, AI massively overpromised and underdelivered, because people didn't understand what they didn't understand. So no criticism of the people, but that is what people looking in from outside saw. So that was what happened there. Then people sat down and said, okay, well, all right, so, sorry, we got it wrong. And then there was this rebuild and more slow progress. So I'm just going to write slow progress here. So it was saying, all right, it's actually much more difficult than we thought. And people sat down and started doing proper research, not just the kind of, oh, look, trick, it works. Oh, look, trick, it works. And rather sat down and saying, what are the things we actually want to solve? What are the things we actually want to do? What are the characteristics of those problems? How can we apply computing to these? And actually did it properly. And this is when we started getting these more useful things. So how do humans solve problems became one of the things that was considered back then. And another thing that came out of this is the whole notion of intractable problems, NP completeness and such. So the first round of AI didn't even understand NP completeness, which you guys have already considered, as far as I know. No. Oh, okay. Basically, it's a very basic theory saying under these conditions, if the thing scales, I think it's exponentially or faster than exponentially, it's non-computable. So people started getting an understanding of this, so the reasons for the over-promising in the early waves started becoming apparent. So this is where progress was actually made, but still very limited by processing power, very limited by what you could achieve. Then we moved on to knowledge-based systems. Yeah, let me write that whole thing out. Knowledge-based systems. So that whole question of how does knowledge lead to decisions, this is primarily what happened here. So you get a doctor and you interview them and try to pull out their expertise as a set of rules, typically. All right? And then you create a system that takes all of those rules and somehow combines them to form an output. Fuzzy logic is one of the things, but it came later. But it's something on this sort of idea. So we've got a whole bunch of rules that say, if this, then that. If this, then that. Which in a diagnostic thing you can sort of see. So if the person is bleeding, deal with that first. That sort of thing. And it looked like this was going to work really well. And again, we found the solution. This is it. AI is going to do everything. Guess what? It didn't. It ended so badly, in fact, that the next stage of AI's history became known as the AI winter. Because a whole bunch of companies had been founded on this technology. Lots of money was put into them. Lots of promises were made based on initial results. A lot was expected. And then somebody realized they're not doing what they actually say they're doing. The technology actually can't achieve that. And when the bottom fell out, it took down a whole bunch of companies and pretty much stopped AI research dead for a while. Okay, the second time, please note, that's important. An example of a knowledge-based system is, I don't know how many of you have memories of Clippy. You've probably heard of Clippy, the Microsoft assistant. That it was this little paperclip that would pop up in everything and tell you what to do. It looks like you are trying to do something. How can I help you? And all it was doing was, if this, then that, and put it together. The only information any user wanted about this thing was, how the flip do I turn it off and make it go away and never come back? And that reaction is kind of emblematic of what happened in this AI winter. People have been promising these things, saying, look, this thing it'll make it so much. Does this sound familiar to anyone? Right, history does rhyme. And it absolutely flopped. In fact, it's now, if you've ever heard of Clippy, it's emblematic of this really cute thing that a company shoved on its users, and its users absolutely hated. Because the technology couldn't do what people said it could. Then, the next major step is we now have neural networks back. Of neural networks. So, the information you need now is a neural network is a model of a brain. Okay, not necessarily a good model, it's just an attempt to create a model of a brain. So at this stage, what started happening, so this is like the early 80s. So the first microcomputers are now starting to become available. People can now get computers at home. So you've now got processing power that is becoming relatively cheap. Yes, it's only got 32 kilobytes of memory, but it's a computer which you can have in your office. Plus, round about the same time, the backpropagation algorithm was developed. Now, the backpropagation algorithm in itself is actually a really bad optimization algorithm. However, the genius of that is there's a way of computing gradients in that is computationally extremely simple. So we had this, people now have processing power available to them, not you've got to queue up to work on the mainframe. You've actually got it and you can work on it. And secondly, a computationally efficient algorithm had arisen. And neural networks pretty much since then haven't really stopped. They've kept going. Now, it took a while for them to achieve the really amazing things, but it gradually continued. So it was this combination of, and again, you can see that relevance of computer science and mathematical developments. Combination of these things led to that. There are problems with neural networks. One of the main ones is they're a black box. You can't figure out what it's doing. So you say you don't know what it is. Yeah, people know what it is, but they don't know how it works. So it is actually still a problem. But neural networks do have a very valuable role to play, and basically since that mathematical problem has been played, you've got things like neural networks, convolutional neural networks, different variations on the same theme. So very important development, started in the early 80s, and as I say, pretty much hasn't stopped. Then we got much more recently, big data. Companies suddenly started realizing we've got information about our customers. And if we use it, we can make our clients spend more money with us. And so this whole question of how do we take this bunch of data, and the data are incomplete, massive amounts of it, not structured, and how do we get something useful out of that? And so machine learning, AI-type algorithms were applied to this to try to get value from this whole bunch of stuff we've got, these numbers we've got stored in a computer. Let's do something productive with them. Sadly, it boils down to sucking more money out of you, targeting the same ad at you every single time you open Facebook, that sort of thing. But that was a major thing in the States, with big data being data mining becoming a standard term. So you've got this mountain of data. How do you get something useful out of it? So, for example, we've got loads and loads of data on students going back decades. Can we do anything useful with it? I wish we could, but so far I haven't seen any compelling evidence to say that yes, we can. So big data was sort of the next big round, and it's kind of, again, kind of the, well, computing power has got so low that your cash checkout is not a mechanical till anymore, it's an electronic thing, which scans your unique loyalty card, which then creates more information about you, which gets stored somewhere. So you can see again how computing capabilities have contributed to this. The last one mentioned in the textbook is then deep learning, and this is very much based on the availability of computing power. So, what's the thing? AlexNet? I can't remember. The first convolutional neural network was somebody who took a GPU and somehow programmed it to perform masses of computations for a neural network, and modified the structure of the neural network to give better results. It was so much better than everything that came before. It was just revolutionary. So much so that NVIDIA went from sort of a niche gaming company, selling graphics cards to people making games, that is now, I think, the most valuable company in the world. And it's basically because people realized we can use this computing that has just been quietly being developed on the side. No one's really been looking at it in much detail, it's just for gamers. And suddenly realized we can take that glut of processing power that we now have access to and essentially take our models, make them 10, 100 times bigger. And just by doing that, we get better performance. All right. And that has pretty much continued to the present day as well. In fact, it has accelerated quite dramatically over the last few years, because now we're not saying, well, get the biggest, hairiest GPU we can. We're now saying, get the biggest, hairiest data center you can, which draws a gigawatt of power. For reference, that's a nuclear power plant, and not a small one. All right, it's going to take most of the water in the area. Yeah. So this whole concept of deep learning, we just have more and more parameters, has taken off. The thing I want to add, because it happened after the textbook was written, are large language models. Now, the current hype around AI actually has surprisingly little to do with what I would consider AI. And it is all about large language models. All right. And essentially, these are ways of trying to get machines to understand language and to respond in language. But fundamentally, if you really break it down, they predict the next word in a sentence. Okay, there's a lot more complexity than that. I must just emphasize that, but that's kind of fundamentally what they do. Now, what is happening at the moment? Well, we've had Microsoft shove Copilot down our throats. Everywhere you go, doesn't this sound really familiar? Everybody just wants this thing gone and off their computer. Doesn't this sound really familiar? We have people telling us that AI will solve all of the problems in the world. If you give the people telling you that, even more billions of dollars. And I really believe that we are on the cusp of, if not an AI winter, then certainly a lot of disappointment surrounding AI. In fact, a lot of the sort of social media reporting recently has been about people standing up and saying, I want no more of this rubbish. Get this rubbish out of my life. I do not want to see AI ever again. It's causing so many problems. Now, yes, that is still something of an extreme view, but I see one or two people nodding, so at least some of you have experienced this, and that's what concerns me here, is that the AI companies, in an effort to get more money, are basically promising the earth. All right. I saw an interview by The Economist, which is a very well-renowned, very, very good publication, very reliable. It was an interview with the financial head of OpenAI. And this person was busy telling about all the amazing creative financing deals that they'd come up with. Now, I'm not an accountant, so please take this with a pinch of salt, but if you have to dream up ways to get people to give you money, that doesn't sound right. Surely if this thing was as good as it said, everyone would be throwing money at you. But no, you've got to find ways to get money in. Yes, sir?
So, OpenAI loses money on every single word that
Yes.
it produces, even on the premium
Yes.
market. And they have $1.5 trillion to spend in this over the next 10 years. And I think their net revenue, not even housing costs, is something like $30 billion.
So you've got a company that's losing money hand over fist, all right, that wants more money than they have, that wants more data centers than they're going to be allowed to build because there just isn't the power generation capacity anywhere in the world. And why? Because AI is going to fix everything. AI is going to do everything. One of the analyses I said is pretty much the only way the current investment in AI can pay off is if every single worker in the United States is replaced by an AI system. That's not going to happen. It's just not going to happen. So are we in a massive hype cycle at the moment? Yes, I believe we are. How is it going to end? Peacefully, please. Because if the market crash happens, so pretty much at the US at the moment is you've got the big six or whatever it is, the big companies all working in AI. And they are making money, well, people are giving them money, which they're then losing, in magnitudes you can't believe. The rest of the American economy is shrinking. They're actually in a recession. Without those six companies, they're right in the middle of a recession at the moment. The problem is, if those six companies die badly, 1930, the Great Depression, is going to look like a holiday. So that's why I say I hope it happens sensibly and slowly, because otherwise we're all going to pay. Now, that should be what happens. But when you have politicians essentially saying we have to fund this, why? Because they told us it's going to do good things. Yet you do realize you're basically giving them money to tell you to give them more money. So I have a lot of concern about where we are at the moment in the world with AI systems. And I do want to emphasize again that the current AI boom is based on LLMs. It is not based on anything else. It's not based on something new that's going to absolutely give us AGI, artificial general intelligence, is one of the things it's bandied about. There are a lot of people who know a lot more about this stuff than I do, who are not being paid to say so, who say this is not going to give us general intelligence. And I think they might be right. So, coming back to this thing, AI has got form on this. AI has done this before. So badly at one stage that the next stage became known as an AI history. So I worry that the current absolute blind push of AI is silly. It really is. But bear in mind, they're not pushing AI, they're pushing large language models. My other concern, the other thing that worries me, is that a lot of the performance improvements we've seen over the last few years since ChatGPT was released have not been to fundamental improvements in the system, have just been due to the fact that we've thrown more data at it and we've built bigger models. There's not actually a fundamental improvement that's been happening, we just made them bigger. Same thing, just bigger, oh look better, give us more money. Yes, and so I have tremendous concerns about where things are going at the moment. However, I must just say, LLMs are amazing. They're absolutely incredible. The fact that you can give them unstructured speech and they can make sense of some of it and give sensible results is mind-boggling. If you had said this 10 years ago, that this is where we'd be today, people would have said, you're a little optimistic. It's real. Will it solve all the world's problems? No. Give me a break. Is it something that we can get a lot of use of? Yes. Are the other AI tools that everyone's now suddenly forgetting about, because this is all anyone's thinking about, still useful? Absolutely. This thing reads my handwriting. And not the semi-neat version I use in class. Yes, by my standards, that is neat. When I write fast in cursive, it can read my handwriting. And it could do that before ChatGPT. That, to me, is where the power of AI lies. So let's stop looking at Those 6 companies that are just working on large language models. And let's look at AI in a more general sense. Let's look at the tools that we as mankind have been developing since the 1950s and see where we can use those things, where we can get benefit from them. And if LLMs turn out to be a good solution for something, use them. But don't blindly just apply them to every problem and hope it's going to solve your problem. So that's why this sort of history lesson is quite important. I hope that all makes sense. All right. Then, let's go with this guy. So, the next question we come to, and this now jumps to chapter 8 from chapter 28 from chapter 1, is there's this concept of weak AI versus strong AI. All right, and this is both partially relevant to our previous discussion, but also very relevant to what we are going to consider AI in this course. So, when we are talking about weak AI, we are saying that a machine behaves intelligently. All right? So going back to that 1950s example, if you could book a flight with a machine that would be an intelligent machine, well, this machine does behave intelligently. By some metric of intelligence, it behaves intelligently, and therefore, under the weak AI assumption, we can say that is intelligence. Are large language models intelligent? Well, by this metric, yes. They do things that would require intelligence. They can understand, well, they can give you a sensible answer if you pose them a question in normal language. So the weak AI assumption is kind of what I like to think of as the sort of the engineering version of AI. Does it do something useful that I can use to get better results? Yes, I'm going to call it AI. Good enough for me. So the weak AI assumption is the machine behaves intelligently. The strong AI assumption is what many people are now trying to push. That's where the artificial general intelligence, AGI, comes from. It's the machine is intelligent. So now we start getting into questions like, are large language models conscious? Crikey, need a philosopher to answer that one. And I must say, from an engineering standpoint, I don't care. All right. I care, can I use this tool to do something useful that gives me a useful result? Whether it's actually intelligent or not is irrelevant. The question is, can I do something that would be useful? So, finding the shortest route from from point A to point B, is that something that can be considered intelligent? Yes, it can. Under the weak AI assumption. Under the strong AI assumption, probably not. So this is a fairly significant thing, and again, I think in the current hype cycle, everyone's busy punting this thing. The machine is intelligent, it's going to exceed human intelligence, it's the next wave of whatever. I don't care. I don't care if your data center based system can do something for me. I want something that is useful to me in the system I'm trying to build today, that'll make it better, that'll lead to better products, better results in the real world. So that's kind of the difference between these two. How do we distinguish between them? That gets quite tricky, because let's take one of the classic definitions of AI. Play a good game of chess. Do you have to be intelligent to play a good game of chess? As a human, yes. As a machine, no. Humanity has very comprehensively proved chess, at least at the level of the best human players, is just a brute force computation issue. You don't have to know anything about chess except just apply brute force and lots of computing power, and you will beat the best human players. I was a student when IBM's Deep Blue beat Garry Kasparov, who was the world chess champion at that stage. And that was a very unfair competition because they never let him see any of his games beforehand. And chess players, even back then, you prepare by preparing against your particular opponent, against their moves. And he'd never seen it play before. But one of the things that happened in this thing, one of the things that apparently broke him, was the one day Deep Blue made a sacrifice. Up to that stage, chess computers did not make sacrifices. In fact, they were the exact opposite. They were very conscious of never falling behind in pieces, in material. And now he suddenly had a computer making a sacrifice. And this apparently just totally knocked him out. And from then on, basically, he just didn't know what to do. Turns out the computer had figured out it was going to win the pawn, it had just sacrificed back with interest, 7 moves in the future, no matter what happened. it hadn't made a sacrifice. Did it appear intelligence? Oh yeah. I mean, if it bothers one of the best chess players, if not the best chess player ever to live, that this machine is doing something that is clearly intelligent, then yes, it definitely satisfies the weak AI assumption. Does it meet the strong AI assumption? No, it can't do anything other than compute lots and lots of chess compositions. All right. So that's why I say the weak AI assumption is better. So there's a task that we look at and say, well, this requires intelligence to do, but it turns out it doesn't. What about the other way around? So the big thing at the moment, or one of the big things, is AI girlfriends. It's just dawned on me. What am I missing here? It's just dawned on me that I haven't heard anything about AI boyfriends, which speaks very badly about men. But anyway, so the assumption underlying this is that you need to have some form of intelligence, emotional intelligence and whatever, for a human to fall in love with, let's again say, an agent, right? Wrong. You should see my son and his teddy bear. So we have to be very careful about trying to say this particular action is indicative of intelligence, because sometimes it just isn't, in the sense that you can achieve that without intelligence, and then sometimes it turns out, well, if you just change the way you frame the question, it's actually dead easy. So we have to be very careful about that. But again, does it matter? Does this definition really, is it really that important to the world? The textbook uses the example, just give me just a few seconds, I've got 3 minutes left. I time it so I know. All right. The textbook asks the example and says, in some languages, what does a submarine do under the water? To my mind, it sails, but in some languages, it swims. Okay? So swim is the same word that you use for a human or an animal or a fish in water. So is that submarine now an animal? And that's the reaction I was looking for, laughter. It doesn't matter. It really doesn't matter. So this whole discussion about whether we're dealing with strong AI or weak AI, I think from an engineering standpoint is largely irrelevant. And the textbook argues the same thing. So it's not just me. So we're going to predominantly be thinking in terms of the weak AI hypothesis, which says, does this thing do things that from the outside look like intelligence? If so, I'm happy to call it AI. And so in this course, we will do things like search algorithms, which is just a mathematical algorithm. We'll do things like optimization algorithms, genetic algorithms. That's just an optimization algorithm, but it does sometimes look like intelligence. We're going to do neural networks, which are an absolutely horrendous simulation of real neural networks, but they display behavior that looks like it's intelligent. We're even going to look at probability theory, because it can display behavior that looks like it's intelligent. So when looking at AI, that is kind of the definition we're going to consider here. And I think from an engineering standpoint, that makes sense. All right, the pre-lecture upstairs. Thank you very much, and I'll see you on Friday.